Hello, welcome. Welcome to SRv6 Algo, the future of intelligent traffic engineering in SR and SRv6. My name is Matt Brenneisen. I'm a customer delivery architect at Cisco. I've been at Cisco about 15 years, supporting SP to begin with, and now I support public sector federal customers. In a few moments, I'll turn this over to Stephen. He'll introduce himself at that point, but we also have a third presenter, Kimrul Islam, who's unable to present with us today, but he was definitely helpful in setting up these slides in the presentation. This is the WebEx app. You guys are probably all familiar with it. If you haven't been auto-joined to this space, please go ahead and do so. It'll be moderated till the end of the week. You can ask us questions. It's moderated by myself and Stephen and Kimrul and a couple other SR experts. So the agenda for today. So let's imagine for a second. We have an intelligent network that adapts to our specific needs, right? We have granular control over every path without the complexities of our legacy protocols. We have the ability to spin up differentiated services in minutes and not hours or days, and we can optimize our application performance on demand and build a truly future-ready infrastructure. And that's basically the 30-second pitch about what this whole session is going to be about, right? So don't get too excited. But it sounds pretty cool, but I think what you'll see is after this session is over, we can do that today with flexible algorithm or flex algo. Is it? Is that any better? He says my audio's in and out. Oh, okay. It's just me then. So we've had a complex balancing act for years now, right? We struggle with the limitations of traditional methods and the overhead of RSPT and the complexity of LDP against our demands of our diverse applications and services. You know, we're always trying to deliver on that SLA we've all agreed to, right? We spend hours tweaking our configurations, battling those suboptimal paths. I know everybody does that. I do, right? But with segment routing and flex algo, it really helps to simplify this landscape. So in a moment, I'll turn this over to Stephen. He's going to give you an overview of flexible algorithm, what it is, and how it applies to SR-MPLS and in the IPv4 infrastructure, and how we can use it today to enhance our abilities within IPv4. Then he'll talk about some on-demand next-hop use cases, ODN. And then I'll talk about SRv6. I'll give you guys an overview of some of the core concepts of SRv6 and some of the benefits you get with SRv6, but then I'll talk about flex algo. This session is mainly focused on flexible algorithm. Then I'll give you some use cases, flex algo use cases in SRv6, and we'll wrap it up with a conclusion and a Q&A. You should have time for that. This slide here covers what we're not going to be able to cover. Understanding segment routing in the SR control plane is important for this session, but we're going to assume a basic level of familiarity with that. Additionally, we're not going to be able to talk about the intricacies of OSPF and IS label transport. Instead, we're going to build upon those foundations and show you how we can use flex algo for that advanced traffic engineering. But some sessions here, I know it's late in the week already, but some sessions here to recommend for you guys to attend. See if I can get this laser to work. There we go. Walk-up labs. I talked to a couple of you guys. You guys said, some people have said they've already started taking these walk-up labs. Definitely encourage you to do that. You'll notice here at the bottom there's a GitHub link. It's a GitHub repository to my GitHub. Throughout this presentation, you'll see a topology that Stephen's going to present, and a topology that I'm going to present on. And that within those topologies, we've spun those up in CML. We built out the entire configurations for you. So you can download those YAML files and spin it up in your own CML environment. You get some hands-on experience and kind of run through this output on your own. So I definitely encourage you to do that as well. So I think at this point, I'm going to turn it over to Stephen to talk about flex algo for SR-MPLS.
Hello? Hello? Can you hear me now? Okay, great. So like Matt said, my name's Stephen Blaisdell. I'm a solutions architect here at Cisco. I've been at Cisco for about 12 years. I work in US public sector with federal customers along with Matt. And this is my third time presenting at Cisco Live, but I do get a little nervous when I'm doing public speaking, so I like to tell a joke before. So I like that joke to kind of have something to do with what we're talking about. And so I was thinking, you know, Matt's talking about SRv6 and I'm talking about SR-MPLS. So I'm gonna try to tell you a joke about IPv6, okay? So why is IPv6 so much faster? Because IPv4 is exhausted, okay? That's a terrible joke, all right? I was gonna tell you guys a UDP joke, but I wasn't sure you'd get it. It's another joke, okay? All right, yeah. This is not a target-rich environment for comedy, right? So I hope. So with that in mind, we got no place to go but up, all right? So hopefully you'll get something out of this. So for my portion of the presentation today, there's really two things that I'm going to want you guys to understand, right? The first thing is, what is flexible algorithm? So what it is, how it works, and the benefits we get from it. And the next thing is, how does this relate to SRODN policy, on-demand next hop policy, okay? So those are the two things. If you get anything else out of this, that's great, but those are the two key main points that I'm going to want to cover, right? But before we jump into it, why don't we take a look at kind of how we got here, right? So some of you, I imagine most of you, are probably very familiar with SRv6. We've been doing this for like 30 years. And this is a good protocol. It works. It does what it's supposed to do. But there's complexity tied up in SRv6. You have to run SRv6, obviously. There's a complex control plane, configuration burden, protocol burden, and it has some limitations, okay? So there's definitely some places we can improve upon that, right? And we got a lot of those improvements when we moved to segment routing and segment routing traffic engineering policy, okay? First thing, one of the major things is we eliminated SRv6, right? So we're left with the IGP and MPLS in the control plane. We get some benefits from that, right? One of those is TILFA, right? So topology independent loop-free alternate. If you guys don't know what that is, if you hear the term like fast reroute, sub 50 millisecond failover, right? That's TILFA that gives us that benefit, right? We also get the benefit of, the IGP, so equal cost multipathing is a big benefit we get from that, okay? We also get the ability to build up that kind of state on the head end, which definitely moves us closer to that like single controller traffic engineering, right? Rather than a distributed system, okay? But still areas of improvement, which leads us to where we are today with on-demand next hop policy. And this is pretty simple, because what we've done is we've taken all that good stuff from SRTE and we've added in Flex Algo, right? That's the main difference. So it's an on-demand dynamic. So when there's a demand on the network, that policy gets instantiated. Dynamic, we can accommodate multiple tail ends from a single head end with a single policy. And we'll see how we do that in the configuration portion. So lots of benefits with that. So this here is pretty much just like a one-page cheat sheet on what Flex Algo is. And we'll dive into some of the details here, but these are some things that are important to understand. The first thing is that a Flex Algo is represented by a number, and this number is between 0 and 255, okay? The first 128 of them, so 0 through 127, these are reserved, okay? So they're either currently defined Flex Algos or they're left for future development, okay? The ones that we can manipulate are 128 to 255. So you're going to see a lot of numbers today when we're going through these configurations, and you're going to see 0 used a lot, and then you're going to see the ones that we're actually manipulating, and those are going to be 128, 129, 130 in some cases, okay? So what can we do with this Flex Algo? Well, we can associate two things with a Flex Algo, and the first is a metric type, okay? So we're not limited to just using the IGP cost metric in Flex Algo, okay? We can utilize the delay metric, the TE metric. We can even utilize something called a generic metric. That's more recent, right? But a generic metric is basically a metric that you can define. So say you have some kind of monetary cost for links or something like that. You can devise a scheme that costs those out and utilize that metric for your path computation, okay? The other thing we have are constraints we can associate with this, right? And a constraint is basically a link affinity, a link color, okay? So I can choose to include or exclude links based on some type of policy. So if you can imagine, maybe you have something that needs to remain in country or in a certain region, or if you have something that needs to only traverse encrypted links. So you have MACsec enabled across a path, you can color those links in a way that makes that possible, okay? The other thing is Flex Algo. This is all carried through the IGP, be that ISIS or OSPF. We're not running an additional protocol here, okay? So what do we get from this? Well, there's two main things that we get. And the first thing is network slicing. And so what we mean by network slicing is being able to take our topology and create sub-topologies that consist of only a subset of those nodes within the topology, okay? And the other thing we get is that path computation based on our requirements, okay? So if we have delay-sensitive traffic, we can utilize a delay metric, and we can constrain that to certain links. So network slicing and path computation are the two things we get from Flex Algo, okay? I mentioned there's some currently defined flex algos, and there's currently 2 of them, and you're going to see a lot about zero today. Is anybody here running segment routing today? Okay, so you have flex algo 0. If you have segment routing, you have flex algo 0. It's the default flex algo, and it utilizes the IGP cost metric, and it does not constrain any links, okay? The only big difference between flex algo 1 and flex algo 0 is that with flex algo 0, an individual node can have a local policy that changes that path computation. In flex algo 1, you cannot. It's strict SPF, right? So whatever the Dijkstra algorithm, you must not change that policy, okay? We're not going to use that one today, but you'll see quite a bit about flex algo 0. So far, I've been talking a lot about flex algo, but really what I want to talk about is SRODN policy. So how does flex algo relate to SRODN policy? Well, there's 2 things when we talk about SRODN policy that are associated with flex algo. And the first one is the flex algo prefix SID. That's how we do our network slicing. And the next thing is the flexible algorithm definition. And that's how we do our path computation. That kind of lays the rules of the road for how this flex algo is going to operate, okay? So let's take a quick look at those 2 technologies. So first, the flex algo prefix SID. That's giving us our network slicing. So this topology you see over here, we're going to see a lot of this today, okay? I'm going to utilize that quite a bit, and it's going to be changed in certain ways on certain slides, but I'll explain it all here. But the big thing about the flex algo prefix SID is it's made up of 3 pieces of information. First is the flex algo. The next is a loopback address. And finally, it is a segment routing label, okay? So if you look at my topology here, I've configured this topology where nodes 0, every node is in flex algo 0, obviously. It's the default flex algo, right? And then the top plane there and the head end and tail end are in flexible algorithm 128. And then the bottom plane and the head end and tail end, 0 and 9, are in flexible algorithm 129, okay? So 2 sub-topologies. That's kind of explained in this chart over here. So what does this look like from a flex algo prefix SID standpoint? Well, if we look at some examples, right, like node 1 is going to have a loopback address, flexible algorithm 0, and an SR label. That's its flexible algorithm prefix SID for that flex algo. It is also a member of 128, so it has a different SR label, same loopback address, so it's a member of 128. Likewise, node 7 here on the southern plane has 2, one for 0 and one for 129. And all of this information is advertised by the IGP, which gives every node an understanding of what the topology looks like, okay? Of who are the other members of that flex algo, all right? Next, we have the flexible algorithm definition, and this is what I told you helps with path computation, okay? So this is where we associate those metrics and those constraints with the flex algo, okay? So what we've done here is, for these 2 planes, I've said, okay, I have flex algorithm 128, I want to utilize the IGP cost metric, and I want to exclude any purple link for whatever reason, right? For some reason, I want to exclude that link. And then for flex algorithm 129, I want to handle my delay-sensitive traffic, and I'm going to exclude the red link for some reason, okay? The important thing about the flexible algorithm definition is that it has to be consistent across the network, okay? Because if one node thinks that you're using the delay metric and one thinks you're using the IGP cost metric, that's not going to work, right? So to make it consistent, we advertise this from a single node. And then we configure that. That's what the flexible algorithm definition is. So in this case, we've selected node 3. And it's going to have those definitions on it. And you'll see how we do this in the configuration. It's really very simple. Jeez. And then we configure a standby FAD as well. Okay? That is also going to advertise the flexible algorithm definition. One thing to note, so the FAD can be advertised by 3. It can advertise the FAD for both 128 and 129. Doesn't have to be participating in 129 to advertise that information, okay? So just keep that in mind. We'll see some of that when we get into the configuration piece. So how does this work from an individual node's standpoint, right? So we have a node N here, and we've done 2 things. The first thing is we've enabled flex algorithm 128. So we've provided with the prefix SID, all of that stuff. And then we've also provided with the flexible algorithm definition, whether it's been configured locally as the FAD advertiser or whether it's been received from another router, it has that information. So it knows two things at this point. It knows what its topology looks like, and it knows what the rules are. It knows if there's been any paths constrained or if they're using the IGP or cost metric, whatever it is. So what this node is going to do is the first thing, it's going to prune any nodes that are not a member of that flex algo, okay? Next thing it's going to do is it's going to prune any links that are constrained, right, that are not part of flex algo 128, okay? The next thing it's going to do is it's going to build a shortest path tree, just like you would with any type of routing protocol, based on what the flexible algorithm definition has said, whether that's the IGP cost metric, the delay metric, or whether you utilize some kind of delay metric. It's going to build that tree. And then it's going to install that reachability information for that flex algo into its forwarding table, okay? So what do we end up with? Well, based on what we've kind of done so far, this is what our topology is going to end up looking like. We have flex algo 0, which consists of all routers, all nodes. We're using the IGP metric, and there's no links constrained, okay? Then we have a secure slice, and I mentioned MACsec, right? So let's say we only wanted to use MACsec-enabled links, and the link between 2 and 4 is not a MACsec-enabled link. So this is what our subtopology is going to end up look like, and we're going to use the IGP cost metric. And then finally, for flex algo 129, we're going to constrain the link between 5 and 7, and we're going to utilize that for our low delay traffic, our delay sensitive traffic, okay? All right. So for these next couple of slides, we're just going to use the IGP metric, and we're not going to constrain any links because we want to kind of show you how this traffic actually flows, right? So for flex algo 0, if we assume that all of the link costs are the same, we're simply going to use equal cost multipathing to route across this network. And the interesting thing here that you'll see is a little bit different. I told you if you're running segment routing today, you have flex algo 0, right? There's no ODN policy associated with flex algo 0. We don't have to define that. And you'll see what that looks like when we get to configuration port. For flexible algorithm 128, you can see we've configured prefix SIDs associated with that, and now we have an ODN policy for flexible algorithm 128. But we're not going to constrain any links, and so traffic is going to equal cost multipath across that plane, okay? Similarly, and this is a little bit repetitive, for 129, we're going to do the same thing, and it's going to equal cost multipath across this southern plane, okay? So let's talk real quick about the binding SID. Binding SID is an important piece, it's an important component to this technology, right? Now, I've said that this is a dynamic policy, it's an on-demand policy, okay? So what we're doing is we're coloring these routes at the tail end, okay? And then we're also creating a policy that matches that color on the head end, okay? When those two colors match, it creates a binding SID. And the binding SID is what is ensuring that the correct traffic is being steered onto the correct policy. Because this head-end router could have 10, it could have 15 different policies, okay? So we have to have a way of binding that traffic together. And we use the binding SID to do this. And it's very simple. This only happens on the head end. This binding SID is used to steer traffic onto that policy, and then it's popped. And then we use the flex algo SID to reach the tail end. Sorry, scoot back a little bit. Push the wrong button to reach the right policy, okay? So this is kind of an example of what I'm talking about here, okay? So we have our ODN policy configured on the head end, and on that tail end, we have this VP and V4 unicast route, right? And we're coloring that with color 800, okay? Then we have our on-demand policy with color 800. So when this traffic matches, traffic destined to that destination, it's going to create a binding SID. And this happens dynamically. You don't have to do this, right? Although you can if you want to, right? It creates this binding SID, and that's what is ensuring that this traffic is steered onto that policy correctly, okay? And this does build to kind of show that. All right. So there's two different types of policies that we can utilize. We have what's called the per destination policy, and this is based on BGP extended community colors. And that's what is shown in this slide. And I'm not going to talk too much about this one because a lot of everything we're going to do when we walk through the configuration is going to be associated with per destination policy. So we'll just skip ahead real quick to the per flow policy. This is one we're not going to configure. You'll see a little bit of configuration for it, but we're not going to dive too deep into it. With this, the policy is based on the packet, right? So I can use QoS markings, I can use an ACL, so I can use DSCP values, and I'm going to assign that traffic to a forwarding class, okay? And that class is, I have 8 of them, 0 through 7, right? And this is all happening at the head end, all right? So it's going to make sense when I show you the next slide, kind of what we're doing here, right? But all of this configuration happens at the head end, which is different than how we do this with per destination policy, okay? So everything we're looking at here is on the head end router, okay? And I have an input policy on the service side of this head end router that says that if I have traffic matched DSCP value 46, I'm going to assign it to this class minimum delay. I have an ACL for some premium hosts, and if it matches that ACL, I'm going to put it into this priority host bucket. And then I have some scavenger class traffic as well. And I'm putting it into these class maps here, right? Okay. Then what I do is, I am coloring my traffic on the tail end. But I'm coloring it with this number, which is going to this per flow policy, which is treating these individuals and assigning them to different algorithms. Now, why would you want to do this? This is more granular control over how that traffic can be handled. It's not based simply on the destination. It's also based on that traffic type, okay? Because, you may have multiple different types of traffic reaching the same destination, okay? So that's per flow policy. And per destination policy, you'll get a very good understanding about that whole thing as we walk through the slides, okay? So at this point, we've covered a lot of the basics of SR-ODN policy. So now we can kind of put this into practice and see how the configuration looks and how it works, okay? So let's do that now. Sure. I'm sorry? All policies active? Yeah, well, if you have, you can, we're just doing one policy. You can have multiple policies if you wanted.
Yes, but why I cannot configure full national policy? This is better sometimes.
Why don't we wait to the end and we can talk when I can, hear you a little bit better. Sorry, I didn't want to walk all the way back there. So, all right, so there's really 5 steps to building this. And the first thing is we need to configure our flex algo prefix hits, right? That's pretty simple. All of this is really simple, actually. The next thing we're going to do is we're going to configure that flexible algorithm definition. The third thing we're going to do is configure that affinity map, which we haven't seen that yet. It's very simple to do. We're then going to do our BGP extended community colors on our tail end. And then we're going to enable our ODN policy, okay? So let's see how we do this. So we have some examples here of how you do this in both XR and XE. What I'm doing here is under the routing process, I'm signaling intent for Flex Algo 128. I'm configuring a prefix SID, okay? So I'm just saying, hey, I'm going to configure something for Flex Algo 128, and then I'm configuring the prefix SID for Flex Algo 128 down there. You'll also notice there's a prefix SID here that doesn't have an algorithm associated with it. That's for Flex Algo 0, right? Okay. If we look at one of these, this is going to be the tail end node, you'll notice it has 3 Flex Algo prefix SIDs configured because it's participating in 128, 129, and 0. The configuration is slightly different on XE, but not terribly so, right? Very similar. So that's all I have to do in order to configure that. The next thing I need to do is I need to configure my flexible algorithm definition. And remember, I configure this on a single router, perhaps 2, okay? And in this case, I'm going to configure this on node 3. This is an XR device. So I'm going to say flexible algorithm 128. I'm going to set the priority because I'm going to have multiple FADs advertised. I'm not going to call out any metric for flexible algorithm 128, which is essentially just means use the IGP cost metric. That's the default, okay? And then I want to advertise the definition. That means this device is advertising it. And then setting the affinity, I'm going to exclude anything including ISP1. I'm also, again, going to do the same for FlexAlgo 129. And notice 3 is not participating in 129, but it's still advertising this flexible algorithm definition. And the only thing I'm doing there is saying I want to use the metric type of delay for that plane. Okay? I would do the same thing on another device like router 8. I would just set up a lower priority there in case there's some kind of failure, right? So now all of these nodes in the topology have 2 things, right? They know who's participating in this flex algo, and they know what the rules are for participating in this flex algo. They know which links to prune, they know which metrics to use. They have everything they need to operate there, okay? So now the link affinity map is the next thing I'm going to do, okay? And I'm going to do this under the routing process again. And I'm going to name these things. I'm going to set the bit positions. The really important thing here is that bit positions have to be consistent of all of the routers within the path computation. The names don't have to be the same, okay? So if I called this FlexAlgo MaxSec on which router is this? Router 1. And I called it encrypted on 3. As long as that bit position was consistent, I'd be just fine, okay? That name is locally significant, but that bit position is not, okay? Configuration is very similar on XE, just slightly different when you assign it to that interface. Okay?
Question.
Yeah.
Do you have to read it?
There's a lot you can. There is a limitation, but I can tell you what it is, but I can get you that information. Okay. So now we're working on our tail end, okay? So we need to color those links with the BGP extended community color, okay? This is pretty simple. Most people here are pretty familiar with XR, RPL, that kind of thing? Okay. So all I've done here is I'm setting a BGP extended community color 100 and 1 to 200, and then matching these 2 destinations, okay? And using RPL to assign those. So if you're in 9.0.0, your color is going to be 100. And if you're in 10.0.0.0, your BGP community color is going to be 200. Very similar, simple. I'm then going to take this, and I'm going to advertise this to my tail end, okay? Coloring those routes. Okay. So now we're ready to go, okay? What I have to do now is I have to configure my ODN policy on the head end, okay? This is really simple. It really just requires 2 commands, okay? For on-demand color 100, I'm going to say dynamic SID algorithm 128. I'm going to say I want you to use FlexAlgo 128. For 200, I want you to use 129, okay? I've done some other things on here. Path invalidation drop. Basically, if there's not a valid path across that, I don't want you to use FlexAlgo 0. I want you to drop that traffic. And restricting I can restrict source and destination traffic that's allowed to use that as well. But you don't have to do that. Really, all you have to do is configure this to make that work. So what's going to end up happening is I'm coloring those routes on this tail end, and traffic destined to 9.0.0 is going to flow over that northern plane. Traffic destined to 10.0.0 is going to flow over that southern plane, okay? But the cool thing I told you about this is I can accommodate multiple tail ends with this policy. So I've got another tail end there, 99, and 99 is advertising similar but different subnets with those same colors. And so this head end can use this same policy to steer traffic across those flexible algorithms. There's another way we can do this with multi-candidate paths, and this is slightly different kind of idea. What I'm doing here is I'm saying, okay, my preference for this traffic, which is color 100, is for you to utilize this MaxSec enabled path, okay? But if that fails, I don't want you to fail over to the FlexAlgo 0, right? I want you to utilize my second preference, preference 90 here, and fail over to algorithm 129. So you can do that as well, okay? That's a multi-candidate path setup. So now let's talk a little bit about multi-domain. Everything I've talked about so far has been a single domain. So I'm talking about a routing domain, so a single routing instance with a single area, okay? But if you're managing a network of any size, you're gonna have multiple areas. You may have multiple instances of routing protocols, okay? And when we do traffic steering, any type of traffic steering, we have to have link state information, okay? And so the IGP has a limitation. It's not really a limitation, it's the nature of the IGP, right? The IGP does not share link state information outside of the area, and certainly not out of the routing domain, okay? So in order to get this to work, there's two things we have to do. We have to redistribute those flex algo prefix SIDs between those domains, and we have to use a PCE, a path computation element, okay? So the first thing I've done here, we've redistributed those, and we've redistributed them on those ABRs there, 3 and 4, okay? So now I have to set up this SRPCE, and this can be some kind of lightweight router, software router works. It's just control plane traffic, very similar to like a route reflector or something like that. Anybody in here familiar with the PCE? Use this? Okay, right. So this is all control plane, right? And what I've done is I've set up a BGP link state relationship between the SRPCE and these ABRs. It doesn't have to be the ABRs, it could be any router in here who's got the link state information, but in this scenario, it's good because the ABRs have information about both sides, right? So I've set up this relationship between the two. Now the SRPCE has a full view of both sides of those domains, okay? I then set up a PCC relationship. PCC is gonna be my head end, that's Path Computational Client, okay? Right down here. And it has a PSEP relationship with the SRPCE, okay? So now when it needs to find link state information, it needs to find a path to something it can't find, it can delegate to the SRPCE. And it's very simple configuration to do this right here. So how does this actually work? This is a bit of an eye chart here. But what's gonna happen is first, the head end is gonna look at its local policy to see if it, yeah. Sure.
The distribute link state, that's required.
Yes.
Okay.
Yes.
Okay. That's
Yeah.
what those are.
Yes. Okay. So, all right, so what's gonna happen is this head-end router is first gonna look at its local policy and see if it can build a path to that tail end. It's gonna find that it cannot, it doesn't have link state information to it, and it's gonna be inactive, right? We see it's inactive here, okay? It's then gonna delegate to the PCE and say, hey, can you build me a path to this tail end? And the PCE is gonna say yes, it's gonna provide it with the labels. And you'll notice there's two labels in this label stack, right? The first label is what's gonna describe a path to that ABR, okay? And then that's going to be popped, and this label is gonna describe the path towards the tail end, okay? So that's the only major difference with multi-domain. Okay, performance measurement. And Matt's gonna talk a little bit about this too, but I've been saying this whole time that we don't have to use the IGP cost metric, right? We can use the delay metric as well, but that's not something that is inherent to the IGP. That's not something it does normally. So we have to provide it some kind of mechanism to do that, and we utilize the performance measurement to do this. And this works probably a lot like you would think it works, okay? Probes are sent out periodically between the routers. They're gonna timestamp it and send, and based on those timestamps, it can calculate what the delay is, okay? So the big difference between two-way delays, we don't need clock synchronization. With one-way delay, we do need clock synchronization. Probably you do have clock synchronization, so that's not a big deal, but that is the big difference there, okay? Yeah.
Is there a way to record historical data for those latency?
So like store that delay information? Yeah, TWAMP, yeah. Two-way active monitoring protocol that everybody heard of TWAMP before, yeah. Mm-hmm. Have you heard of PCA? Have you heard of PCA? Provider Connectivity Assurance? Okay, okay, so that does TWAMP, right, as well. That's what it's utilizing, and it will store that historical data for you as well. Yeah.
Well, this is better.
Yeah.
Because you're doing, it's kind of like doing.
So there is a way to get that delay information, utilizing this delay information from a centralized controller like PCA, or here's the answer, right? Like if you're utilizing some kind of tool like NSO or some kind of programmability, you can really do anything, right? Like you can store any type of information. So my answer would be yes. It's just like how you actually do it, would be the key, right? Sure, yeah. Okay, so the only thing I kind of want to point out on this slide is that when we're doing, what we're basing that computation on is the minimum delay, okay? So we're not using the average, the maximum, or the variance, right? So when you configure this under the routing protocol, the delay measurement, for performance measurement, it's utilizing the minimum delay, okay? Yes?
If I want to use a delay constraint,
Use a what?
the constraint delay. Right?
Yeah.
So
The metric delay. Yeah.
I need the performance monitor.
Correct. Yep. That's how it would utilize it. That's how the IGP gets told to include that information and how it measures it, right? So, yep. Okay. So I'm pretty much at the end here. I'm going to turn it over to Matt to talk about SRv6, but I did want to talk briefly about the CML that I've provided on that GitHub link, okay? It's very similar to what we've done here today. The only thing I did was, for those top planes and bottom planes, I minimized one of the routers, both for you guys, for resources, and also because the guy who runs my CML thing was yelling at me, because those XRVs are a little heavyweight, right? They take some resources, so I was chewing up a bunch of his resources. So anyway, all I've configured here is pretty much the groundwork for you. There's 2 flex algos, well, 3, including 0, right? These are both head ends and tail ends on node 7 and node 8. And there are service routes shared between them that are colored. And the reason I didn't utilize delay or anything like that or constrain any lengths, and the reason I didn't was because I didn't want you to just go in there and be able to do a bunch of show commands. You could actually go in there and change things. You could configure your own flex algo, constrain lengths, change the metric type, use performance measurement, all of that stuff, right? So if you want to do that, the README file is still being updated, but if you have any problems with it, you can definitely reach out to me, and I've had a few people pull it down, and it's worked, but if there's any issue with it, just let me know. I haven't had widespread testing on that just yet, so. All right? Okay, with that, I will turn it back over to Matt.
Thank you. So far we've been talking about SRMPLS using IPv4, obviously using MPLS in the data plane. This part of the session is going to be on SRv6, particularly flex algo for SRv6. Is anyone in here familiar with SRv6 yet? Anybody running it in their network? Nice, got one person. I fully expected everyone to raise their hand. So there are several sessions, of course, at the beginning that I kind of pointed out that you can get some SRv6 basics or some hands-on experience with SRv6 and some walk-up labs. So I definitely encourage you guys to take those sessions or audit them after Cisco Live is over. You can download those sessions. And if you're also familiar with dcloud, you can also get some SRv6 hands-on experience on dcloud.cisco.com. Let's talk about the data plane instantiations for segment routing. So you got 2. You have SRMPLS, which we just talked about. Use the MPLS in the data plane. A segment is encoded with an MPLS label. Then now you have SRv6, which uses IPv6 in the data plane, and one or more segments is encoded within that IPv6 address. This is really the reason and the main difference between SRv6 and SRMPLS, and also the reason why SRv6 is more streamlined and efficient, right? Stephen talked about how SRMPLS allows you to eliminate RSVP. Well, SRv6 allows you to eliminate MPLS, right? It's just the next evolution, right? So let's talk about why MPLS was developed to begin with years ago, right? 25 years ago, late 90s. MPLS was developed because they're trying to combine the efficiency of layer 2 switching with the scalability of layer 3 routing. You guys might remember we used to call MPLS layer 2.5 because we're using layer 3 routers to do label switching. And MPLS has been great. It's worked for us. Been using it very well, and there's still a lot of development going into that. But there's certain things that SRMPLS does not have natively. For example, there's no native VPN mechanism within MPLS, so develop VXLAN and GRE, and you guys might remember IP over IP. There's no native traffic engineering, so SRv6 was developed. And then later on, started getting into service chaining, so NSH was developed. And these are all these different constraints, so these shim protocols that were developed to, on top of a workaround that, which was MPLS, right? So the problem is now, what if we need to go between these domains? Well, now we have a data center that does VXLAN, needs to go through a gateway that does protocol conversion to convert that to an MPLS, right? Across these different domains. So each one, so those gateways, what do they do for us? Deep packet inspection, protocol conversion, bottleneck, scale, reliability, cost, not just monetary cost or operational complexity. So these challenges are kind of what led to eventually led to the creation of the SRv6 microSID. Sometime between 2013, 2016, they started developing this. They developed these with specific pillars in mind, right? They wanted to make sure it's backwards compatible. So you need to make sure that it can be used on any IPv6 device, right? Wanted to make sure they eliminated those shim layers, right? Those SRv6, LDP, NSH, things that aren't needed, right? Because they want to natively support these different features. They want to have a cohesive, unified IP solution from end to end, right? They want to be able to put this in any domain. So a quick overview, some of the core concepts of SRv6. Again, this is not an SRv6 deep dive. This is just kind of some of the improvements or some of the benefits that SRv6 has over SRMPLS and SRT in general. So we know segment routing in general is a good approach because that's why SRMPLS is developed, right? But now we're combining the principles of segment routing with IPv6, that source-based routing, and then the native capabilities of IPv6 and the IGP. And the native capabilities of IPv6, what I'm talking about is that long 128-bit address, right? We'll go into that here in a moment, how that really helps us out. And the native capabilities of the IGP, the scalability and the summarization we get with IGP. Because as you're going between these different gateways with MPLS, you have to advertise those /32 host routes. Well, with IGP, you can just summarize. With SRv6, we're now summarizing again. You really achieve some great scalability or regain the scalability and the gains you had before. It also makes network programming easier because you're using that 128-bit address. And I'll show you how we're advertising for an SRv6, you're advertising a 32-bit locator. In SRv6 Flex Algo, you're advertising a /48 locator prefix, and that leaves you 80 bits to work with. Put those extra functions in there, those extra microsids, so you can actually encode that policy at the ingress to the network. So you have a lot of network programming capabilities there. And of course, the simplification. We're eliminating a lot of protocols, MPLS label stack, SRv6 and LDP, like I said. With the overview of SRv6. So the micro instructions, like I said, they're embedded directly within the packet at the ingress of the network, or we're using a segment routing header, an SRH. An SRH is basically like, you already have 6 16-bit functions available within an SRv6 microSID. An SRH is like if I need more. So that's another IPv6 packet immediately following it. To date, there's really only been a few, there's quite a few SRv6 deployments, but there hasn't been any use cases for anything more than 6 of those functions, but the capability is there. And then all it really adds is like a next header function within the SRv6 packet that says option 43. There's a segment routing header behind me if you need additional functions, right? So by being able to do this, SRv6 is able to eliminate the need for the label swapping, right? And the MPLS label stack. Of course, we're streamlining the traffic forwarding that way. And we have that enhanced control because we're able to provide up to 6 functions natively and additional with the SRH. And we're using that source routing. And we also have greater versatility because we're supporting all these services natively. And we also have that scalability because we regain that capability for summarization and scalability with the IGP. Quick slide here. On the left, you have the SRMPLS label stack, or the SRMPLS protocol stack. And on the right, we have SRv6. And you can see how on the left, under the transport protocols, we have BGP labeled unicast for SRMPLS, which is interdomain label transport. We have RSVPTE, LDP, and IGP. And on the right, we're just left with ISIS v6 with SR extensions. Of course, you can use OSPF v3 for this, but our session is focused really on ISIS right now, so I just put that on the slide. And of course, in the data plane, utilizing MPLS for SR-MPLS and IPv6 for SRv6. That's the key difference right there. So, going to get into some real meat of the topic here. What's being displayed here is the SRv6 flexible algorithm locator SID. You can see at the top here, you have the locator function, which is 48 bits and followed by 5 16-bit functions. But let's talk about for a second the SRv6 microSID. It's not displayed here, but we're going to kind of compare the differences. The SRv6 microSID, for those taking notes, is RFC 8986. And it consists of 3 parts: the locator, the function, and the argument. The locator is just, I'm the destination and it's advertising. The function is, you have 6 16-bit functions that say, what's the path you want to take to get there that you want to impose upon the ingress, at the ingress, using a policy. And the argument, those bits are rarely used, but they're for like additional endpoint functions. And you can see here with the Flex Algo locator SID, we have a 32-bit microSID block, and we have a node ID, and that node ID just denotes what node is advertised in it. And you have, it's a /48, and you have that green TT, which indicates particular participation in a particular flexible algorithm. You see right here we have some example locators for node 1. In our topology, I'll show you, we have node 1, and it's really the one we're mainly configuring, but they're all configured in that CML topology file I left for you. But you see here I have Flex Algo 0, which is FCBB BB00:1/48, and Algo 128, and Algo 129. So we'll point out a difference with SR-MPLS and SRv6. Now, it's not strictly required to configure Flex Algo locator prefix in SRv6, but it is recommended, right? So you definitely configure locator prefix. And then also some of the differences, both are 128-bit, like I said. SRv6 uses a 32-bit locator followed by 6 16-bit functions. A couple other things to point out here is the private address space in use for these locator prefixes. It's FC00/7. That's common and recommended. You can use, you can come up with your own microSID space, but that's the one that's recommended. It's private address space, so you get benefits of not being globally routable, right? So you have enhanced security. It's also very, very small. The private address space in use is a very, very small portion of the overall IPv6 private address space. It's something like less than 1/2 of 1%, so it's pretty efficient address utilization. And I think one other thing to point out here, and I'll show you why it's important in a couple of slides. There's a concept of the global microSID and local microSID. Global microSIDs meaning the microSID is globally unique within your IGP domain, and local is it's local only to that specific device. And the difference is what they start with. So a global microSID will start with 0 through 9 or A, B, C, D, and a local microSID will start with E or F. And that local microSID, like I said, is specific to that node. So any node can have that microSID starting with E or F. It's just only local to that. And I'll show you why that's important. Does all that make sense for everybody? Yeah, you had a question?
Yeah, just you've got the node ID there picking up 4 ends.
Yeah, it's 16 bits.
16 bits. I've seen other documentation where they had talked about set IDs. Is that
How many?
set? The first 2 characters would be.
Yeah, so you can actually go up to higher. I mean, you're flexible to do that, but in this situation, for Flex Algo locator SIDs, it's a /48. But to your point, in SRv6, you can actually minimize the functions, and you can manipulate that a little bit, right? So this is, let's talk about the shift and forward process. This is how an SRv6 speaker would actually process an SRv6 packet as it receives it. So in the top, what we have here, we have 4 routers advertising the locator prefix for Flex Algo 0. Router 1 is FCBB BB00, which is the Flex Algo 0. 0100, the node ID, and it's a /48. Each one are advertising their respective locator prefix into the IGP. And this allows the source to construct a path known as a function that says, how do I get to my end destination, right? So move down here to the gray portion of the slide. You see router 1, the incoming destination address for router 1, and it has those 4 locator prefixes there, or 4 functions that the source has imposed upon that. Router 1 receives that incoming destination address. It recognizes itself, does a longest match lookup, recognizes itself as the local prefix. It strips that 16 bits out, shifts the packet 16 bits to the left, and adds 16 zeros to the far right. And then does a second lookup, and it finds the /48 now in its table, that it recognizes in its routing table. puts that out on the wire to forward to router 2. So the important thing is that it did 2 long mismatch lookups there when it processes the packet, but that is done at line rate. Right? So router 2 receives it, does the same thing, shifts the packet 16 bits to the left, forwards this packet out to router 3. Router 3 does the same thing, forwards that packet out to router 4. When router 4 receives it, we'll go over what router 4 will recognize itself the local instruction. It'll decapsulate the packet and process the endpoint function based on the segment that it's told to do. And I'll show you how you identify that here in the next couple slides. But this is just important to show you how the actual SRv6 speaker actually shifts and forwards the packet. Does that make sense for everybody? So let's talk about some use cases. So pretty simple, use case, service chaining. Everybody's probably familiar with service chaining, but it's really just ordered service delivery, right? I'm going to impose a particular SID list on my packet, and I want it to process these particular services. So, some examples you might want to use this for, in security service, if you're routed through a firewall or anti-malware service before it forwarded onto the eventual destination, or you can do it in cloud services, or maybe even an SD-WAN. But you might be thinking to yourself, well, I know you said earlier the SRv6 did has 6 16-bit functions, so can I use service chaining use that for service chaining only? Actually, you can, right? But a couple things to point out. We're talking about Flex Algo, so I want to use Flex Algo. But another thing is Flex Algo is actually a pretty efficient way to do that. And you kind of want to specify the path it takes based on your desired metrics and constraints, taking into consideration, the location of those service functions, right? So let's dig into that, how that actually works. So here's where I'm going to bring up again the concept of the global microsid, start with a 0, and the local microsid, start with an E or an F. So what happens here, when router 2, because this is the packet that router 2 is going to see, when router 2 receives this, it's going to say, 0200 is me, and I have 3 local functions behind that. So it's going to know immediately it's going to have to process that. And it'll do that in one long as a match lookup, because those local functions will exist in its routing table. So it's going to do a lookup, and it's going to see all 3 of those functions at once. And this is also important to talk about from an SRv6 service chaining perspective. There's a concept of SR aware and SR unaware services. SR aware means the service is going to process just like an SRv6 router would, where it's going to receive the packet, recognize itself as a local instruction. It's going to strip it off, do the shift and forward process the service as it would, and then forward it on to the next destination in the SID list. But there's SR unaware, which basically means it's going to need an SR proxy because it can't process SR packets. So SR unaware is more common, and that's the one we're going to talk about here. And what that means is, in our case, let's say there's an SDN control plane not on this slide, and it says, hey, any packet going from router 6 destined for router 7, I want you to impose this particular policy on this at ingress. And the policy will say, impose this path on it with these functions, right? So router 1 is going to receive it. It's going to forward it on to router 2 based on its longest match lookup. It's going to see 0200. It's going to find a /48 in its routing table. It's going to forward it on to router 2. Router 2 receives it. It's going to receive this packet just as shown above. It's going to do a longest match lookup, one longest match lookup, and it's going to recognize itself as the local instruction and the 3 local functions to process. So router 2 will now cache the SR encapsulation. It's going to send the packet, a plain packet, onto the DPI, the DPacket inspection tool, which will process and return to the SR proxy. Then it's processed and then repeated for the IDS and firewall. And R2 reapplies the cached SR encapsulation and forwards the packet onto the next destination, which is router 3. Router 3 receives it. All it has for router 3 is FC, BB, BB01, 0300, right? Followed by a long string of zeros. When you in an SRv6 or Flex Algo for SRv6, when you have a long string of zeros, that just means end of packet. And it says process this packet as you would the endpoint function as it dictates, and I'll show you what the endpoint function is. In this case, it probably says drop it off into this VPN or VRF for router 7, right? Does that make sense for everybody? So disjoint path, most people are familiar with that, right? But what is a disjoint path? It's just you're going from point A to point B, and I want to take different ways to get there. I want to, on this path, I want to use this, physical link and these links, and on this path, I want to go this way. It's for critical redundancy of critical applications, right? So the topology Stephen went over, we were already going over disjoint path and didn't know it. So one of the common use cases for dividing a topology like this into a dual plane topology is to enforce disjoint path. A lot of you guys are probably already familiar with disjoint path from an SRTE perspective. If you're familiar with SRTE, you already configure disjoint nodes under the constraint. So you might be familiar with this already. Just wanted to kind of point that out. I didn't want to dive deep into this one. It's more of a simple use case, but it is a valid use case. So I thought this slide was really interesting. I stole this one because in SRTE, currently, out of 100% of the use cases for SRTE, FlexAlgo can account for about 90% of them. So it's a very powerful tool. You can see there's some extreme cases, extreme disjoint path, there's a bandwidth optimization that can't be accounted for with flexible algorithm, but still, you can count for about 90% of your SRTE use cases with flexible algorithm. So we're going to get into the configuration for SRv6 FlexAlgo. We're going to use these steps, but I'm just going to jump right to the next slide to kind of go into this, into the process of the steps. So see here, this topology, routers 1, 2, 3, 4, and 5, it's an ISI SV6 topology. It's configured just as you probably would expect, or address family IPv6. Each device is advertising a source loopback address, just as you expect IPv6 to work for ISIS. Now, how do we actually configure it? So, the bottom here in the middle here, you'll see FlexAlgo 0. Routers 1, 2, 3, 4, and 5 are all configured for FlexAlgo 0. This is their locator prefix. There's an X there as my variable. Obviously, it depends on which node I'm in. So if I'm in router 1, I'm going to use the 1 there. If I'm in router 2, I'm going to use a 2 there, and so on, right? And the top half of my network, routers 1, 2, and 3, they're all configured for FlexAlgo 128. And then the bottom half of my network is all configured for FlexAlgo 129. Now, the notice routers 1 and 3 have all three FlexAlgos, 0, 128, and 129. So now how do I configure this? From a segment routing perspective, you go SRv6 is global. I've got my source address. You notice the source address is just like a traditional IPv6 loopback address. It's actually recommended to do the, take it from your existing locator prefix space, but in my implementation, I did not do that. So that would be like an FC or FB right there. And then you identify your locators, you call it out. I've called out locator main, which is my FlexAlgo 0. And notice here I didn't specify a particular flexible algorithm. I didn't say algorithm 128 or 129, so that's using the default FlexAlgo 0. And I assign my locator prefix, which is my /48. And I assign my locator down here for locator latency, and it's BB01, which corresponds to algorithm 128. Now, and the same thing for chain, this is my service chain function. And right here, you'll notice also the microsegment behavior. That's just, what do I do with this packet? What's my local behavior? So there's two options. You have behavior PSP-USD, which is if you're the penultimate segment and you recognize a string of zeros at the end of segment, I process this packet, I decapsulate and send it on to my ultimate segment destination, if that's what the endpoint dictates. Or ultimate segment decapsulation, I decapsulate the packet and process the packet as end of function. That's what that means. You also have another method called shift only. We're only going to do shift and forward and just forward and on, right? But this is the default way, and you configure that. So over here, now we've advertised all of our locator prefixes, or configured them at least, throughout each router. Now let's go ahead and advertise this into the IGP. So you see up here for router 2, that's very light, but it's focused on router 2 there. Under the ISIS process, I said FlexAlgo 128. I specified metric type of delay, and I'm advertising my definition. Same rules apply in SRv6 as SRMPLS. You have to advertise the definition on at least one device. And you also specify the metric type. You don't have to, you can just use the IGP metric if you want. But there are, those 4 different metrics you can use that Stephen went over. Then, address family IPv6. I call out participation for that address family for my 2 particular flexible algorithms, 0 and 128, or main and latency. And I did down here for router 4. The same thing, FlexAlgo 129, I specified advertised definition, of course. I didn't specify the metric, so that means I'm going to use the default. And then I specified under address family IPv6, SRv6, I called out these 2 particular FlexAlgos again. So, in essence, what I've done is I've made a southern plane and a northern plane. One of them is using 0 and 128. The other one is using 0 and 129. Does that make sense? Sure.
It can't be a loopback where it can carry this.
So you can assign a locator prefix for every particular flexible algorithm, and it looks like any other IPv6 address within your space. So you need a locator from an SRv6 perspective because each one of those is associated with that flex algo and how it behaves within that device. So you can now route to that specific locator from any other point on the network.
Can't it be a loopback?
So no, to answer your question in short, it can't be a loopback because each one of these is advertising participation or advertising from a particular flex algo's perspective, from a segment's perspective. It's not, this is my device, because this device could have multiple flexible algorithms or multiple segments it's behaving for, up to 12, I think. So that's why you have different locator prefixes for each. So now that we've configured it, advertised it in the IGP, how are we going to route traffic to it, right? There's multiple ways to do it. I'm just going to show you one quick way with BGP. With IPv6 or with SRv6, you can actually encode this directly via CLI on the ingress devices. You don't need to use BGP. You can use an overlay like an SDN control plane to impose a policy directly onto the, into the IPv6 address. You can use SD-WAN over the top of this. But just quickly, from an IPv6 perspective, from BGP perspective, let's say we have multiple VRFs, right? I want to use a particular flexible algorithm per VRF, like you have this CE device, or this could be a service that's existing in a data center. So I've specified under the BGP process, I called a VRF called low latency, and I'm saying I'm calling it out under SRv6 to use my locator latency. My allocation mode is per VRF. And then for my VRF main, I said my locator is main, my allocation mode is per VRF. So now whatever interface or service I put in within that VRF low latency will now use the flex algo latency or 128 across my network. Now what if I want to use multiple flexible algorithms per VRF? Then use to build a route policy. In this case I called it mix, and my example is I said from router 1's perspective, anything going to the IPv4/32 for R7, I want you to set an allocation mode of per VRF, how you want you to use the locator latency. Otherwise you're going to fail over to, or you're just going to use the VRF main, locator main. And then I called it out, that route policy under the SRv6 process for that VRF in BGP. Now, anything I put in that VRF, if it matches that, 777/32, then we'll use the latency. Otherwise, it's going to use the main or flex algo 0, which means it can use the entire network, right? Did you have a question? No, sorry. So some other options, right, for routing traffic from an SRv6 flex algo perspective, I kind of talked through them a little bit. We talked about 5 a lot. We talked about using the IGP. We talked about policy-based traffic engineering. I did mention explicit configuration on the source node. There's some ideas on how you can route traffic onto the flex algo. So now how do we validate our configuration? You see here, this is from router 2's perspective. So router 2, I'm doing this command, show segment routing, SRv6, SID all. And you see it has the 2 flex algos configured, latency and main. And you see my segment ID over here. And my segment ID is FCBB BB01:2. That's the locator prefix for router 2 for flex algo 128. And you see it says behavior is UN. UN stands for locator prefix. And my local behavior is what we configured, PSP/USD. And beneath that, you can see these additional /64s, those are UA, stands for local adjacency. And the local adjacency isn't going to be instantiated until you've advertised within the IGP. Because what's happening here, once you do this, once you advertise the locator prefix within the IGP, XR is going to be streamlined for you. It's going to actually create a local adjacency for each interface that's associated with that flexible algorithm. In this case, we have gig 0000, 128:P. The P stands for protected because we've already configured TILFA in our topology, and I'll show you how to do that. So each one of these /64s, you'll notice that it starts with an E. That is locally significant to that device only, but it will appear in the routing table. So the routing table for another device will show this, FCBB BB01:2:E000 as a /64 to be able to be reachable within your domain, right? But only router 2 will locally process that. You can see down here for flex algo 0, we did the same thing, and it has, flex algo 0, protected path, right? Does that make sense? So you break down that output. This is from router 1's perspective. You see I have it's just a summary configuration, right? What flex algos do I have configured in router 1, 0 through 0, 128, and 129. Here's my name, here's my prefix, and the status is active. It's just a quick way to look at the configuration you have in each router. So I'm not going to go into this too much, but this is just the logic that each SRv6 node follows as it builds out its subset virtual topology or flex algo. You overlay your metrics and constraints on top of the existing IGP topology, and it builds that subset virtual topology like a flex algo would. This is just the logic each node follows. This is just here for your reference. So this is a lot of output, right? I'm sorry for the small font, but I did truncate this. I'm sure most people are familiar with the ISIS database when you're doing troubleshooting from an IPv4 perspective. So what is the ISIS database? It's the perspective of the entire IS domain from that router's perspective, right? So in this case, I'm using router 2. And router 2 is looking at the output. It's looking at router 1. So let's kind of break down this output. I want to show you how to break down this output. So you see locator in red. So up here in red, you see my SRv6 locator. It says it's FCBB/BB01:1/48, algorithm 128. So from router 2's perspective, it sees R1. It sees the locator prefix. It knows it's associated with flex algo 128, right? So you can see that. Now look at the capabilities, right, in blue. You see from the capability perspective, it says your SR algorithms you're participating in are 0, 1, and 128. So router 2 knows that flex algo, that router 1 is participating in those three flexible algorithms. And I just skipped the slide, sorry. Now let's look at the end. End is end SID. It says my end segment ID is FCBBBB01. That's my locator prefix, so you see UN there. And my local behavior is PSP/USD like we configured. Now the endpoint function, this is what I talked about earlier, n.x. There's multiple endpoint functions. There's like, I don't know the exact number, there's at least 10 to 15 of them. And they say, what do I do with this packet when I get there? And you can, that's determined by the end segment. N.x is like, cross-connect this over to a local interface, FCBB/BB01:1E000. You guys remember in the previous slide in validation, I said this is a local adjacency interface that was instantiated after the locator prefix was configured in the IGP. So there's a reference slide in the back of this deck. I forgot to mention there's tons of reference slides in the back of this deck, but there's one specifically for endpoint functions. It will go over exactly what these end functions mean. There's end.x, end.dx, there's end, which is the basic endpoint function. There's DT4, and those all dictate, do I drop this into a VPN? Do I put it on an interface? Do I give it to a local adjacency, and so on? In this case, you can see it's n.x. It's Algo's, says it's a local adjacency for Algo 0. And see, here's my, now we're going to talk the SID structure. That's that burnt orange looking color. They said that would show up better than yellow, so that's what we did. So you can see here the block length is 32, and the node ID length is 16. So hopefully by now you recognize that as the F3216 format. So that's another way, a quick way to see, oh, this is a flex algo locator function because it's block length of 32, node ID length is 16. So that's the 3216 format. Does that make sense for everybody? Cool. All right, so Stephen talked about delay metric configuration, and he was absolutely right. You do, the recommended way is to let the IGP, or to dynamically configure it, and then have it dynamically be configured using, or figured out using TWAMP, then dynamically update that into the IGP, which is not what I did here, right? I did this for a reason. I'll show you in the next slide. But you can see what I did. You configure the performance measurement under the interfaces, and all nodes that are participating in it. And I specifically said gig 000, I want you to use delay metric 5,000, 5 milliseconds, and for 001, I want you to use 100 microseconds. Now, if you remember our topology's configuration, the top half was the low latency, and the bottom half was the service chain function. So if I specify 100 microseconds for the bottom half, all things being equal, what would normally happen is if I'm using the delay metric, it would go this path, right? Because that's the lowest delay path. But because I'm using flex algo and I've created virtual topologies, what's actually going to happen, as you see, show performance measurement interfaces for gig 0001. The advertised delay is 100 microseconds, as you'd expect. But then you look at the Ceph table for VRF1 for my end destination, and it's going to say gig 0000, which is it's going that way. And the reason why is because that's the only path that's actually participating in my low latency flex algo. So I created a subset virtual topology. It's not even going to take into consideration that other path anymore because it's not part of that virtual topology anymore, right? But like I said, all things being equal, if I was using flex algo 0, or if I specified router 5 to participate in flex algo 128, it definitely would have taken that path. let's talk TI-LFA from an SRv6 perspective, Flex Algo perspective. So we all know what TI-LFA is. We want to be able to get that sub 50 millisecond failover. We want a backup path already existing in our routing table because we want to be able to get to that backup path without convergence. We don't want to have to wait for the router for the IGP to converge, right? So from a Flex Algo perspective, what it does when it builds that backup path, it builds that backup path based on your desired metrics and constraints you've defined within that Flex Algo. So it's not going to fail back to Algo 0 or fail back to the IGP because it really can't, because it shouldn't be aware of that topology because you could end up with routing loops based on your configuration. So how do you configure this? Just like you'd expect, fast reroute per prefix TI-LFA and all interfaces and all devices onto the IGP. And now all of our devices are configured. Now how do we validate that? You can see here, from router 2's perspective, show ISIS IPv6 fast reroute for the locator prefix for router 3. You see here it's a backup path TI-LFA, interface 0000. My protected node is R5. And then if I look into the Ceph table for the locator prefix from router 2's perspective, the locator prefix for router 3, it says it's backup TI-LFA, and my repair node is router 4. So in summary, kind of what we're saying with TI-LFA, if the path between routers 2 and 3 were to fail, router 2 has to be able to reach the repair node already without convergence, and that repair node has to be able to reach the eventual destination already without convergence, right? That's how we're going to get that sub 50 millisecond failover. And you can validate it with those two output commands. Does that make sense? All right. So this is my CML topology that I built. I only put this slide in here because Steven put one in for his. so you can see here the top half is green for low latency, and the bottom half is the red for service chain function. You can see my router 1 here. I did show segment routing, SRv6 locators. I have the 3 locators configured in there. Again, I definitely encourage you to take advantage of this. I've configured the BGP in there, configured ISIS. The Flex Algos are configured, but I definitely want you to tweak those configurations and look at these config outputs on your own time and really spend some time there. So we're starting to get towards the end of the deck here. You can see as we start putting up slides that say services supported, right? We're not going to dig deep into these specific ones, but these are the services you'd expect for SRv6. We talked about layer 3 VPNs a little bit, and layer 2 VPNs. So I know SRv6, at the beginning when I asked who was familiar with SRv6, not a lot of people raised their hands yet, but it is already a very mature technology. We talked about some of the specific RFCs though. We mentioned RFC, well actually we talked about flexible algorithms, which is RFC 9350. I didn't explicitly call that out yet, but that's the RFC for flexible algorithms. We also talked about SRv6 network programming, RFC 8986. I also briefly mentioned the segment routing header, SRh, that's RFC 8754. Cisco's been involved in authoring or editing most of these, or if not all, because some may realize that Cisco actually is the one that developed SRv6 and brought it out to the community. From an ODN, on-demand next hop support highlights perspective, these are the services that are supported there. These are for reference, so you can refer back to this and make sure you have support. And from a Flex Algo perspective, these are, we talked about a lot of this. We talked about OSPF and ISIS, now they support it. We talked about the SRv6 microsid and data plane monitoring. So this slide here is how we can stay up to date with existing segment routing technology, new technology. Has anybody seen that segmentrouting.net website yet? It's a great resource, for sure. And at the bottom here, there's 3 segment routing books, part 1, 2, and 3. Segment routing, part 3 is based on SRv6, and I think chapter 4 is on Flex Algo. I've been using that a lot in the last couple months. So I definitely encourage you guys to look at those. And here's the GitHub repository we talked about a few minutes ago. So we talked a lot of material today. I kind of want to just give a brief summary of kind of what we talked about, just so everybody can, make sure you leave here with the, with the highlights. We discussed Flex Algo and on-demand next hop, right? We talked about next hop with SRMPLS. Then we did an overview of SRv6 and SRv6 Flex Algo. Remember what Flex Algo is? It's just an IGP extension, right? It allows us to create multiple virtual topologies within the IGP. And Flex Algo allows us to choose the metrics and constraints that we deem important, not just the default IGP metric. Remember what those metrics are. You have the delay metric, the IGP metric, the TE metric, and now more recently we have the generic metric. Stephen briefly mentioned that. You remember how do we configure that? We have to configure a flex algo definition on at least one device in our domain, probably 2 for redundancy. And that applies with SRMPLS as well as SRv6. Then in SRMPLS, we configure that prefix SID. Then in SRv6, we have that locator prefix, right? So ways to continue your education. We also talked about, remember, the challenges of traditional methods, and we discussed the simplicity that FlexAlgo brings to this. We hope you see that by now. We talked about SRv6 and how it's more efficient, and you can eliminate those shim protocols, how it streamlines your network architecture. We can build that truly future-ready infrastructure today. It's not just something we were kind of wanting to happen, it's actually here now. So we really encourage you guys to use these resources. And we'll have quite a bit of time here for some questions if you guys have questions, but definitely encourage you to utilize these resources. Also use the walk-in labs. Join the WebEx Teamspace if you haven't already done so. And more importantly tonight, before we get to that, do your session surveys, right? And then tonight, have fun tonight at the appreciation event. I heard the band is killer, right? So that's my only joke I got. That's literally it. So thank you guys for joining us.